Thank you. For the final session, we're going to have two 20-minute talks with questions for each, and then we'll have our 3 lightning talks. And there'll be no questions in between the lightning talks. The questions can come afterwards as we prepare to go to dinner. So for the first talk, we have computational scientist at the numerical algorithms group, Wadud, Miah. And he's going to talk about the verification of Fortran codes. Thank you very much.
Thank you, Matt. As Matt mentioned, I'm from the numerical algorithms group. I'm also a presenter at the Fortran Modernisation Workshop, which is a series of workshops that's been running across the UK to help people modernise their legacy codes. It also talks a lot about good practice in code development, including verification. The Camfort team based here, including Dominic, Mistral and Matt, are also one of the presenters of the workshop. And what I've been doing with this workshop is I've been gathering lots of data from the participants who attend. So I give them a pre-workshop questionnaire and they fill in lots of questions. And after the workshop, they also fill in a post-workshop questionnaire. And I've managed to collate a lot of data, and I think it shows, it says some interesting things, some of it a bit debatable. So I'll talk about Fortran compilers. So one of the questions I ask the attendees is, what compiler do you use? And this shows that the GNU is the most commonly used compiler, probably because it's free, followed by the Intel compiler because it's a very high performant compiler for Intel CPUs. And it also lists some other compilers, PGI, Cray, Petascale, and the NAG Fortran compiler. And one of the things I've noticed about compilers, again, this is debatable, is that compiler vendors are either very good at high performance, or they're very good at good verification features. And compilers tend to fall in between, and that's been my experience. So clearly the Intel and GNU compilers are top of the list. So how good are they at verifying Fortran codes? This is a URL which has a list of synthetic Fortran codes that deliberately have bugs in them. And all the compilers have run these synthetic codes with bugs. And this is a table that shows the percentage of success rate. So we can see G-Fortran and Intel have 53% success rate in detecting bugs in these synthetic codes. And for me, I think that's quite a low percentage. Whereas the NAG Fortran compiler, you can see it has success rate of 91%. And when I first came across this table, I was actually quite surprised that the Intel and GNU Fortran have very low success rate. And you look at PGI, which was another compiler that was also used, and that has even a lower success rate of 28%, which is pretty low, I think. So compilers are one of the tools that you can use to verify codes, and the other are static analyzers or automated verification tools. And one of the questions I was asked by the Camfort people to put in the questionnaire was, do any of the attendees use any automated verification tools? And out of 155 respondents, only 11 developers say that they use automated verification tools. And again, that's, I think, quite a low percentage. So my question is there an over-reliance on using compilers to detect bugs? If there is, and people are using Intel and G-Fortran, then that might say something about the quality of codes that are out there. And of course, the advantage of using verification tools or static analyzers is that they're quite quick to detect obvious bugs. You don't have to run a code for hours and hours and days to realize that there's a bug in a code. That's something that a static analyzer can do quite quickly. One of the questions I ask at the end of the workshop is, what are the topics that interest the attendees of the Fortran workshop? So there's a number of topics that I discuss in the workshop. So you can see PF unit, which is a unit testing framework, for Fortran, and Camport, which is a Fortran verification tool that the team developed here, they feature quite low, I think, in the topics that interest them. So one of the conclusions that I've made is that there's anecdotal evidence to say that testing is one of the least interested topics for Fortran programmers. And Fortran, of course, is one of the most, well, it's a very popular programming language for computational science. So is that saying something about computational codes that are out there? So I'll leave that to you, but I've made my conclusion. And again, this is a view that is also shared by a colleague in the US who also runs modern Fortran codes. And I think one of the reasons why is because you pick up a Fortran book. Which Fortran book covers testing and verification? Hardly any. They just keep talking about the language specifics, how to write do loops and if statements, and think that that's all that's needed to help people write good code. So obviously computational scientists want correct code, and they want fast code. As a colleague talked about earlier, people want fast machines and they want codes to run quickly because there's no point getting result of a simulation of weather one day late because it's absolutely pointless. So the answer to that is to really use an error checking and a high performance compilers in tandem with automated verification tools. Static analysis tools do still have limitations, and and that should also be used with runtime checks, because static analysis tools they never give false negatives. Sorry, they give false negatives so that they can capture errors, but they can miss them as well. And that's why you need to do runtime checks to make sure that there aren't any bugs in your code. So the suggestion is to use unit tests and to build your code with a NAG Fortran compiler with optimization switched off. As a colleague earlier mentioned, that optimizations can change things a bit. And the NAG compiler flags you can use for all kinds of checks are shown here, and I'll go through one by one a bit later. So this is a verification workflow that I would like to suggest. So integration tests should also, for integration tests, you should build your code with a NAG Fortran compiler, and I'll explain this workflow here. So right at the beginning, you have your verification tools. So this is static analysis tests, and examples of that are Camport, ForCheck, and FBT, and I'll talk briefly about ForCheck and FBT. Then build your code with a NAG Fortran compiler, so you can do the unit test and integration test with NAG Fortran. And once all your tests have passed, then you can use a high performance compiler such as Intel, IBM, or Cray compilers, and then you can hopefully have fast and correct code. So what are the verification tools for Fortran? I mean, there's lots of verification tools for the various other languages such as Java, C, C++, but the tools for Fortran don't seem to get much coverage, never mind being taught in a systematic way. So the tools that are available are Camport, which is developed in Cambridge, which stands for Cambridge Fortran, I think. Is that correct? Yeah.
Something like that.
Then you have FPT, ForCheck, and NAG Fortran compiler. And there's also a PF unit, which I briefly mentioned, which is a unit testing framework for Fortran codes. And if you're interested in any of these tools, there are some web addresses at the bottom, and these slides will be made available, so you don't have to rush and try and write the long URLs. One of the real difficulties that I had, I'm going to just show you synthetic codes which static analysis tools and the NAG Fortran compiler can detect. But what I really wanted to get was real example codes to make it interesting, because everyone's seen synthetic cases, and they're like the hello world of error checking. And I really struggled to get real use code, real industrial codes that have bugs. And I asked my colleagues, can you please give me a few? I can completely anonymize it, change the variable names and change the subroutine names. And I can just say it's an engineering code. And I just couldn't get anything. People are so edgy about displaying to the world that their code has a bug. So unfortunately, I couldn't get that many. I only managed to get a few real-world test cases. That's one of the things I find with a lot of vendors is they don't want to talk about the bugs in their code, and they don't want to talk about performance issues in their codes. So this is an actual real bug in a helicopter dynamics code, and this do loop here calculates the lift of a helicopter, and this has a bug. And what this bug did was that it overestimated the lift by 25%. And the helicopter was built, and it was much later that they realised actually there's a bug. And the bug is that the array index is missing. And then they had to go back to all their helicopters, to all the people that they sold it, and they had to refactor it. And obviously it was very, very expensive. So obviously this was a Fortran 77 loop, and the modern and the correct version is you can use array notations, and that will get rid of the bug. Ideally, you should try and use a Fortran 90 array operations as much as possible, because you can introduce subtle bugs in using the do loop equivalent. The FPT tool can detect something, a bug like this. There's some precision bugs that can happen. This bug was this is actually a real bug from a weather modeling code, where they do the raise to the 2/3. Of course, 2/3 is integer division, which always calculates to 0, and they couldn't figure out why the radius of all their hailstones were 1 square meter. And there's various other precision bugs here. You can see this is single precision. This number is just way too small, cannot even fit in the denormalized version. And there's mixing of precisions here. These are real bugs as well, so there's a potential loss of precision. The left-hand side is single precision, the right-hand side is double precision. You can suffer serious truncation errors. And this is the standard way of doing double precision. Please don't do what he showed earlier on in his unified model code. So again, this is another mixed precision code. The left-hand side is double precision, right-hand side is single precision. You will get single precision result even though your left-hand side is double precision. Compilers, I think, are quite poor at spotting precision bugs. A lot of people think it compiles, it runs, it must be correct. Well, not necessarily. I think compilers have improved over the years. I think Fortran can detect one of the bugs, which is if you're doing, I can't remember which way around, whether it can detect this or that, but it can't detect the other. And Forcheck is actually a brilliant tool to detect these kinds of precision bugs. You really should not be mixing and matching the single and double precision. So I'll talk about Forcheck. Forcheck is a static analysis tool. You can just run it on your code, and it will give you. It's very, very rigorous. You probably get really fed up and angry with it because it always complains about everything. But it's good because ideally you want to be able to spot bugs as early in the development cycle as possible. So this is an example of using an optional argument. Here I'm just using it unconditionally. I'm just saying a equals b squared, by not checking to see if it's present. So it really should be using the present intrinsic function to see if the user has actually passed it. If I run Forcheck on this, it will say optional dummy argument unconditionally used. If you run that in production, in runtime, you'll get a segmentation fault. I always encourage people to use the intent keyword. It's a good way to scope your dummy arguments in your Fortran subroutines. If you're missing an intent keyword, you can tell Forcheck to check that the dummy argument has an intent. If it doesn't, it should say dummy argument has no intent attribute, and it will suggest what the intent should be based on whether it's on the right-hand side or the left-hand side of an assignment. It also does actual argument checking. If I go back to my dummy subroutine, you can see A is intent out. If I then pass it a literal statement, not a memory location, i.e. a variable, for check will also complain about that. So it's an invalid modification. The actual argument is a constant or expression. If you run that at runtime, you'll get, I think you'll get segmentation for it, if I'm correct. Again, this is another quick way of checking that your arguments actually match up. As I mentioned, static analysis tools are a quick and easy way of detecting bugs, but they're very conservative, meaning that you can get false false negatives. If they say there's a bug, then they're usually correct. But static analysis tools, they can be limited, especially if you have very deep branches. Obviously they can't calculate the outcome of the branches, particularly in multi-scale, multi-physics codes. So ultimately you need to run it at runtime to check whether there is any bugs in there. And the Fortran compiler, it's a very rigorous error checking compiler. And what happens if it does encounter a bug in your code, it will stop with a very helpful error message and not just a segmentation fault with hexadecimal addresses as to where it crashed. And that way it can hopefully help you debug your code. So with, I mentioned this example before, if I call function foo without b, and I compile it with the -c present, and I run it, it will say reference to optional argument, which is not present. So this is much better than sigsegv with some hexadecimal address that you get. It can also detect dangling pointers. So an example of a dangling pointer is that I declare a pointer which points to an array. I deallocate that vector, so that one-dimensional array, and I then print vec p. Obviously, it's not pointing to any memory location because it's been deallocated. You cannot check this. You cannot check this bug in static analysis because it's quite complicated. So what the Fortran compiler does, it says reference to dangling pointer, target was deallocated, and it tells you at which line. The Fortran compiler is the only Fortran compiler that can detect this bug. Intel and all the other compilers cannot detect this, as far as I'm aware. And there's this undefined variable detection. A lot of people will say, oh, that's quite obvious. If I say real : A and I'm using variable A without assigning it, compilers can detect this. But there are more subtle examples. So what if I declare a variable array 1 to 11, and I say array 1 to 10 equals to a value, and I then print 1 to 11, it's very subtle. Compilers cannot detect this. Whereas a Fortran compiler, if I compile with -c undefined, it will say a reference to undefined variable 1 to 11, and the program will terminate with a helpful error message. And there's also, it can do, if you're passing a constant into a subroutine, which I'm then changing, you can see here the variable x is a constant, a parameter, and in the subroutine, I'm changing the value. If you run it at runtime, again, you'll get a segmentation fault because you're not supposed to be changing that memory reference. If I run it with Fortran compiler, it will say dummy argument x is associated with an expression cannot assign. So that's very useful. You can also have integer overflow tests. Integer overflow tests usually happen when people are moving from 32-bit integers to 64-bit integers for array indexing. So Fortran can detect that. It will say give a runtime error, integer 32 overflow for this expression, and the program will terminate. I think DL poly was verified using the Fortran compiler when it went from 32-bit to 64-bit integers, so it can model a larger number of molecules. So just to wrap up, I know I've got a couple of minutes, hopefully I can do that. I think really more needs to be done to make code verification in computational science a mature practice, just as it is in computer science. And I mean, there's a lot of people developing codes out there, and not many people are really, they don't really have a good verification workflow. And what could be done is that you can, oops, not too far, we can, perhaps a HPC service or a central verification service can offer verification as a service. So, a service like Archer or what's the Rutherford Laboratory have a software engineering service. They could perhaps offer verification as a service where you can give them a code, they can verify it and return it back to you with reports. And also promote verification tools at Centre of Doctoral Training Centres, HPC services and computational science events and groups. And one of the things that I've found a lot, particularly within universities, is that they always teach programming language. And I think that's sufficient. I think it's completely insufficient. Code developers really need a lot more support. And one of the things I found at a conference, and there was a vendor that was selling, I can't remember what the code was, it might have been a CFD code. Whenever they distribute their code, they actually give a report of all their unit tests and a static analysis test with the code. So I think that every community code should openly publish the results of their unit tests and tool verification tests to tell people, this code has been quality checked, so you can rely on this code. Because a lot of people do give source code out quite freely, but why don't they give the results of the unit tests if people want to be really open? And that's the end of my presentation.
Thank you very much. Any questions?
So you mentioned a bit about the balance between some compilers are fast and some compilers are well tested, or draw out the bugs. I was just wondering, with thoughts of verification of the service, do you know if there's anybody who actually uses the very careful compilers for the purpose of testing and identifying bugs in the code, or for production using Fortran or Intel for speed?
Well, I don't think Fortran is a very high-performance compiler. It's, Intel is. I don't know anyone who does that. I know the practice of using two compilers is actually encouraged because that increases the portability of your code. Because you're not being locked into one vendor. But it is the practice. It is something that I actively encourage, is to use two compilers. There are people who are using two compilers, but that's just for portability. But I don't know of anyone who's actually using a good verification compiler with a high-performance compiler. It's something that I think people should do.
On your table at the start of the different compilers that passed or failed these tests, what's the overlap between, so Fortran and Intel are both 15%? Is that the same, or are they almost completely different in terms of the ones which are, are there some tests which are more likely to be caught and others which are a bit more esoteric?
You can get the details from this URL. You can download the source code actually and run it on your own compiler if you're happy to see how good it is. But I don't know if they failed on the same test or not. So going back to your point, you can see that this is the third column, tells you the runtime. So you can see it is taking a lot longer because obviously it's doing more checks. So what if it took more longer? I'd rather wait longer than to get code that I know works.
Any more questions? Go ahead.
Can you go to your this helicopter example with the loop?
Oh yes.
Mm-hmm.
Oh yeah.
So I was wondering. I mean, this is correct code, right? It just doesn't implement what
exactly.
the user thought it would. So does it look for patterns of things that are probably something that the user didn't intend to do, or?
Who would say?
I mean, if you wanted to spot such a bug automatically with a verification tool or anything, right, how would you go about doing this? Because it is correct code.
Instance code, right? it ignores the first assignment.
Yeah. It's
That could be true.
it's-
Could be what you wanted.
Yeah, but there's no good reason to do that. It's more probably a mistake than.
It's perfectly valid Fortran. There's nothing wrong with
Then
it.
you would need some kind of library of behavior that is probably not intentional or something. That it
Yeah.
goes like you have something
Like assignments which are immediately over.
Well, that's a good point. Sorry, I'm just going to wrap up. I mean, this example here, the developer of FPT, actually, he spent his whole lifetime developing this tool, and he's verified a lot of codes, and he's found lots of dodgy things that people have done, and he's catalogued them. and he's put this in FPT to detect dodgy code, and he's also verified Eclipse, which is Schlumberger's Fortran 77 code, which is millions and millions of lines of code. So it's, you have to rely on people who develop these tools.
May I just make one thing? This is an example where the language design, I think, is something that really can contribute to this bug because it allows this silent overloading, whereas I think more statically verifiable languages would not allow this. You have to be explicit about your overloading, and then it catches it right away. But that's what we have to deal with. So, thank you very much.